everyone, this is Mrs. Jackson. This is a very quick video on rational exponents. When you hear the phrase rational exponents, I want you to think fractional exponents. In order to explain that, I'm first going to review the power on power exponent rule. What do I mean about the power on power? Let's take a look at an example here. Let's say 5 squared, and that is all raised to another power, let's say cubed. And so here's the base. 5 squared is our base, and it's being raised to a power of 3. So if I write that out, I have 5 squared times 5 squared times 5 squared. There are 3 of these. And if I further wrote those all out, I would have 2 5s here, another 2, another 2. So what I end up with is 5 to the 6th power. And so if we take a look at what that generalization is, then we have a base raised to some kind of power, so I'll say m raised to some kind of power a, all raised to another power b, and we can see that that would be the same base raised to the product of those powers, a times b. And you can see the reason why. We're just writing it out, and you can see that I'm going to end up with 3 2's, and that is their product. All right, so let's just take a look at an algebraic example, maybe x squared times y. Let's use a negative exponent, negative 3, all raised to the 4th power. This is x squared to the 4th power is going to give me x to the 8th, and I've got y to the negative 12. That negative exponent just says move it to the denominator, so I have x to the 8th over y to the 12th. Okay, so how does the power on power rule relate to fractional exponents? Well, the main takeaway here is that radicals are exponents. That's the main thing. And exponents are radicals, if you want to look at it that way. So we know, when we've been using this property quite often, let's say we had the square root of 5, and we wanted to square that. We know that the squaring is the inverse operation of this radical, right? The square root. Squaring is the inverse operation of square root. Why is that true? Well, we've got square root of 5 times square root of 5. That's the square root of 25. And that is 5. So we can see that square rooting or squaring a square root undoes each other. They're inverse operations, and we just end up with 5 back. Likewise, let's say we wanted to take the square root of 64, which is 8 squared. We know that square rooting a square should give us back 8, right? Square root of 64 is going to give us back the 8. So they just undo each other. They're inverse operations. And so how does that relate to fractional exponents? Well, in fact, that 5 is really being raised to a power of 1/2. So let me write that out. So that square root of 5 is really 5 raised to the power of 1/2. Why is that true? Because if we have our exponent rules, if we have 5 to the 1/2 times being raised to another power of a square here, power of 2, and that's all I'm doing. We know that the power on power rule says that I would multiply those powers together. So this is 5 raised to 2 times 1/2 is 2 over 2, or just 1. And typically we just drop an exponent of 1. And so I want you to make this connection here between these two rows. That square root, and you know, you've heard me say that we got lazy in math. Square root, we use it so much, it really has an index of 2 here, but we square root so often in math that we've dropped the 2. That really is a power. It is an exponent of 1/2. And it has to be in order for our power on power rules to hold. So if I square root that radical, it really must be 1/2 because I have to multiply these together to get back a 1. Now what about other index numbers? In other words, what about a cube root or a fourth root, for instance? So if we take a look at a cube root, we know that I'm going to use a perfect cube, which is 4 cubed, right? That cube root here should be the inverse operation of this cube. They would undo each other. We would expect to get the 4 back out, right? So, and we do. This is actually the cube root of 64. And the cube root of 64, or 4 cubed, is 4. So they just undo each other. So what does that look like from an exponent point of view? This is 4 cubed under the radical, and this radical here is a fractional exponent of 1/3. So our power on power rule says that we would multiply those exponents together. So I would get 3/3, or just 4 to the 1. And typically we just drop that 1, and we get 4. So a cube root is a fractional exponent of 1/3. I'll do, take it to the extreme. If I had x here, and this is index of 5, this equivalently would be x to the 1/5. All right, let's conclude this video with 2 different examples. I'm going to start out with an algebraic expression with a fractional exponent, and I'm going to say write this in radical form. First off, we can kind of break this apart. This is x squared raised to a power of 1/3. You can think of it that way. And if we look at it that way, then we can say x squared, and this 1/3 is a cube root. All right, so that's example number 1. If I said rewrite this radical in exponent form, maybe I'm just making up problems here, maybe 5th root of x to the 3rd, y to the -2. Let's throw some negative exponents in here. That is x cubed y -2 to the power of 1/5. That is power on power, multiply those powers, x to the 3/5, y to the -2/5. And if I said I only want you to use positive exponents, then we can rewrite this as x to the 3/5. That stays in the numerator, and I would have to move the y's down to the denominator because of that negative exponent. So hopefully this quick video helped pull this together. Rational exponents, fractional exponents are actually really a simple concept if you just think about that power on power rule. Thanks for listening. Hope this helps.